12, we're going to make license plates. Trying to figure out how many possible license plates there are. First, we're going to pick 2 letters. Then we're going to pick 5 digits. So we're practicing the fundamental counting principle, which basically means we first look at the scenario as a sequence of events or choices, decisions that have to be made. And then we figure out how many ways can each of those decisions be made. Part A, it says repeating is allowed, which means this is a possible license plate. A and A can, well, A can appear twice. And digits can have a 1, 1, 1, 1, 1. That's allowed. In scenario A, where repeating is allowed. But part B, repeating is not allowed, so if we pick A here, we can't pick A, so we gotta pick something else. If we pick 1 here, we can't pick it again, we can't pick 1 or 2 again, we can't pick 1, 2, or 3 again, we can't pick 1, 2, 3, or 4 again. Okay, so there's a possibility. So repeating is allowed, repeating is not allowed. Which one do you think will come out to be a larger number? You can repeat, which means we're not limiting our possibilities. Okay. So these are just examples. So first we have to be able to, without me just telling you, list it out and say, well, the first thing that happens is going to be this. So what's the first thing that we're going to do? First thing we're going to pick. What's that? The first letter? Going to pick a letter. What's the next thing that's going to happen? Pick another letter. What's the next thing that's going to happen? Letter. Then we're going to pick a digit. A digit. A digit. A digit. And another digit. All right, so let's go to the letter. The first letter that we choose, how many do we have to choose from?
26.
There are 26 letters in the alphabet. What about the second one? 26, because we can repeat letters, so it's perfectly okay to pick from any of the same 26 letters from here. How many digits do we have to pick from? 10, because 0 makes 10, right? 10, and 10 again. 10, 10, and finally another 10. So you multiply all those together, and you'll get your 67,600,000 license plates. But in this scenario, we're going to pick a letter. We're going to pick another letter. Then we're going to pick a digit, and another digit, another digit, another digit. We're going to do the exact same thing, but we're not going to allow repeating. So first letter, how many choices do I have?
26.
26. Nothing's happened so far, so I can pick anything. But the second letter I can't repeat, so how many choices?
25.
25. If I choose A, I can't choose A here, so I have B through Z, that's 25 letters. And same if I choose B or C or whatever. I just don't allow that to be a possibility in the second choice. How about digits to start with? But then I don't have the whatever I picked here for this one, so I have 9. In this one, I can't choose either of these two, so I have 8 choices, 7, and 6. We multiply all those together, because the first choice is one of 26 letters. There's 26 branches. Say I choose A, then I choose my next letter. Well, there's going to be 25 branches coming off of there. Okay, each one of these is going to have 25, 25, 25, all the way down. So far, just for 2 letters, we have 26 branches times 25 branches is going to be whatever that is. Then we pick A, and then say we pick B. And then we need to pick a digit. Well, there's 10 coming off there. Each one of those is going to have 9. Each one of those is going to have 8, 7, and 6. So we have 26 times 25 times 10 times 9 times 8 times 7 times 6, because every one of these branches is identical to this one. It has all that many branches, lots and lots, too many to actually draw out. That comes out to be 19,656,000. Okay, another question?
48, what's that equal to?
8. 10.2, right?
Yes.
Oh, there it is, right there, okay. So, remember this problem is we're gonna get 3 CDs. We're gonna get 2 contemporary CDs, 2 of those, 1 classical CD. And we want to pick our 2 CDs from the contemporary so that they're not both the same. So they're not, well, here we go. We're gonna pick a blues CD, and we'll pick a jazz CD. Okay, so the CD will be Entirely Blues, and it's a new fusion of music and jazz. Blues CD and a fully jazz CD. All the tracks are jazz. Okay. How many ways from those 5 can we pick 2 CDs? First, we're going to pick 2 contemporary CDs. How many contemporary genres are there to choose from? 5. How many do we want? 2. We want to choose 2 of them. Doesn't matter which order we put them in. Why not? How could you describe it to someone who doesn't quite understand that? Why does it matter what order we pick them in? It's not what?
It's not like a sequence or anything.
There's no sequence. I don't need a first CD and a second CD. If I pick these 2 CDs, I just have them. I have those 2. When you look at your CDs at home, if you even have CDs anymore, then you look at them and you say, well, it doesn't matter what order I have them in. If I put this one on top or this one on top, there's still I have these 2 CDs. So order doesn't matter, so we use combinations. And so that's how many ways there are to pick 2 contemporary CDs. So however many ways they are, you've just found all of them. Next, we're going to do what?
Times it by 3.
Pick what?
Times that by 3.
Times that by 3. Why times that by 3?
Because there's 3 options in classical and
And you only pick 1. Yeah, so pretty simple. We just want to pick 1. Pick 1 classical CD. That's how many ways there is to do that. Now, if we wanted to pick 2 of them, that would be, well, still 3. Because if you pick 2 CDs out of 3, it's like you're not picking 1 CD, right? How many ways are there to not pick 1 CD? 3 ways, right? When I choose opera, I'm automatically making a group of 2 by default. Right? That's why 3C1, which is what we just did, is the same as 3C2. Like when these 2 numbers add up to this number, they're the same as far as combinations are concerned. When you make a group of 1, you're automatically making a group of 2. Here, 5C2 would be the same as 5C3, because 2 and 3 add together to make 5. When I pick 2, I'm automatically picking 3. They're just the leftover group, but they're still a group of 3. So kind of a neat thing about combinations. Whatever 5C2 is times 3. 30. That'd be 30. There you go. Other questions?
Can we do 18? 10.2?
10.2 to 18. Five-card at least one. This is a lesson in something called complements. Complements, as in geometry or combinatorics or whatever we're talking about, the two complements add together to, well, make some kind of a whole. When we're counting, complements are all the possibilities. Okay? Let's talk about that. What does it mean to get at least one spade? One out of five is a spade. Is that the only way to get at least one spade? What if you have two spades? Is that at least one spade?
Yeah.
So you can get exactly one, exactly two,
3, 4, and
exactly 3, 4, and 5. All of those fall under the category at least one, correct?
Yeah.
There's 13 spades. There's 4 suits, but each suit has 13 cards. So we can get one spade, we can get 2 spades, we can get 3 spades, we can get 4 spades, we can get 5 spades. With the way that we understand how to count, we can count those things. Exactly one, exactly. So you can count how many ways are there to get exactly a certain number of whatever, 3 out of 5 or 2 out of 6, whatever. So what we have to do is count how many ways can we get exactly one, right? That's some number of 5-card hands are possible with exactly one spade, all right? Exactly one, not also 2, 3, 4, and 5. So then we'd have to count 2, all the hands that have exactly 2 spades, exactly 3 spades, exactly 4 spades, and all 5 spades. And then what would we do with all those numbers? Add them all up. Those are all the hands that all have at least one spade. Okay, so let's just start in the middle with 3 spades. We're going to have to count it anyway. So the first thing we could do is get 3 spades. Right? You get 3 spades. And then next we have 2 things that are not spades. Okay? The way we say not in math is with this little symbol right here, a line with a down mark like that. So 2 not spades. Okay, so let's count the ways that we can get 3 spades. Exactly, like how many ways can we take 3 cards out of the spades and group them together? How would we count that?
13.
I'm going to choose out of 13. That's maybe a little bit of a tricky thing for everyone to realize. If we want to get spades, we just want to limit our number to 13 because there are only 13 spades. We want to make sure that things that we're taking out in groups of 3 are guaranteed to be spades. So we just limit it to the 13 cards that are spades. And we want to choose 3 of them. Does order matter?
No.
No, so we use combinations. So that's how many ways there are to get 3 spades. We count all those. And then we multiply it by how many ways there are to get 2 not spades. How many ways are there to get 2 not spades? We're going to make sure that we take 2 cards. What's that? 39. 39 are, that's how many not spades there are. Right? So we want to, again, like we want to guarantee that these cards are spades, so we take only from spades. We want to guarantee these are not spades, so we take only from things that are not spades. We take them in a way that order does not matter. We take 2 of them at a time. That's how we count that. So we multiply that together. All right, so that's for 3. Now let's do for 4. We want to get 4 spades and 1 not spade. How many ways are there to get 4 not spades? Or sorry, 4 spades? 13.
Combination.
See, 4. How about to get 1 not spade?
39.
Just 39, right? There's 39 cards. You can take them one at a time. It's easy to count that. Go down the line, 39 of them. We could do 39C1, but that's what 39C1 would be. It would be 39. And down here, we just want all 5 of them to be spades. We want none of them to be not spades. So let's just count the spades part, right? 13C5. And we'll come up here with 2. This will be 13C2, 39C3. And this will be 1 spade, so how many ways are there to pick 1 spade? Well, there's 13 ways to pick 1 spade times 39C4 to choose 4 not spades. Hold on, don't do all that work yet, because this is a lesson in complements. This is a lot of work. It's not an unimaginable amount of work, but it would take a few minutes. We take this, multiply by that. All right, set that aside. Take this, multiply by that. Set that aside. Set that aside. Set that aside. Set that aside. We add them all together. We'd be done. And that'd be how many ways there are to put together a hand that has at least one spade, meaning 1, 2, 3, 4, or all 5 spades. Okay. What is the only other possibility as far as 5-card hands are concerned with spades? Isn't there another possibility? So we have looked at all the different ways that we can get 1, 2, 3, 4, or 5 spades. Is there a different number of spades we could possibly get? Just in the whole wide universe?
13.
No? There's only 5 cards, so we can't get 13 spades. We can only get 5 cards. Huh?
0.
Yeah, no spades. Okay, it doesn't fit in the at least one, but that is the only other possibility. Right? So that is the complement. 0 spades is the complement to at least 1 spade. Either you get 1, 2, 3, 4, 5, or 0, and that's everything, right? Any card or any hand you pick at random will fit in one of these. Right? Can you think of any hand that wouldn't fit in those? Either it's got 1 through 5, or it's got no spades. Okay. Well, this is probably a lot, right? Probably more than this, because this includes all the just all the other hands. All right. But that's all the hands. That's every single hand. So if we can count this, then couldn't we just take that away from all possible hands? Take all the hands. Well, let's kind of establish that this is all the hands possible. So if we take all the hands possible, and we just take away that part, scratch that out, this is what's left. Right? All of 1 through 5 spades. So let's figure out how we get 0 spades. We'll take that away from the total number. Of course, you're going to have to count the total number of hands. We've already done that before, though. So let's count how many ways are there to get 0 spades. Well, that's just all 5 cards are not spades. How do we count that? 52. 13 of those 52 are spades. We don't want any spades. 39 combinations of 5. Right? And combinations of 5, I want to choose from the 39 that are not spades. So I want to take that away from all the cards. Now, how many 5-card hands can I possibly make out of all the cards? 52. C5. You take all the possible combinations and just take away all the possible hands that don't have any spades. So you can see how there's this dividing line between 0 spades and at least 1 spade. They could have asked a different question. They could have said at least 2 spades. Okay, that would have divided it up like this. At least 2 spades means 2 spades, 3 spades, 4 spades, or 5 spades. So we could still use the complement. It would still make our work a little bit less time consuming, because we could just count this, add them together, take that number away from the total. If they said at least 3 spades, well, now it's almost a wash. Because I could either calculate this or this. But if I calculate this, I'm done. If I calculate this, I still have to subtract it from the total number. So maybe it would have been faster if they said at least 3. Totally different question, not related to this per se. Then it would be faster maybe to just calculate this. If they said at least 4, it would be easy to just calculate the 4, the 5, and add it together. But you want to be thinking about that. If it seems like there's a lot of calculations involved, maybe you should look at the complement, and that applies to probabilities too. And say, what's the probability, the probability of getting a hand with at least 1 spade? Well, let's calculate the probability that you'll get no spades, and just take it away from 100%. Any questions about that? Questions about anything else? All your questions are answered?
14.
10.2?
Yeah.
Okay. Cool. Four kings and 1 other. Okay, you can see 2 things are going to happen. I'm going to pick 4 kings, one other card. Count the ways we can pick 4 kings. Count the ways that we can pick one other card. How many ways are there to pick 4 kings? Oh. What?
16.
16 ways?
4.
4?
There's 4 kings.
There are 4 kings, so there's 4 ways to pick 1 king. How many ways are there to pick all 4 kings? 1. It almost seems too tricky. But yeah, there's only one way to pick all 4 kings. Now there's more ways to pick, say, 3 out of the 4, 2 out of the 4, 1 out of the 4. But if you pick all 4, there's only one combination of all 4 kings, and that's all 4 kings. Right? Or if we didn't think of that, we could just think, we're picking out of 4 kings, there's only 4 kings. We're picking them in a way that order doesn't matter, and we're picking 4 at a time. Right? If you were to plug them in your calculator, it would just come out to be 1. Anytime you do this, where these numbers are the same and you're doing combinations, not permutations, but combinations, is always what? There's only one way for that to happen. Pick all of them. How many ways are there to pick one other card that's not a king?
48.
48. There's 48 cards that aren't kings. We're only taking one of them, so we don't have to really think about all the different combinations of 2 or 3 of them. Just one of them. So we go down the line, we pick all 48 of them. Those are all the possibilities. Or if we weren't thinking about that, too in depth, we were just in our combinations mode. Let's see, we'll shrink this down. So I know 48 is the total cards that are not kings. Do it in a way that order doesn't matter, and I'm going to choose one of them at a time. But that's just going to come out to be 48. So similarly, NC1 is always just whatever n is. Because you're choosing from this one at a time, so there's that many ways. But anyway, so it's just going to be 1 times 48. So 48 hands that have all 4 kings.
It's a lot easier than this one.
Yeah, it usually is with combinations and permutations. I was just at a math teacher's circle last night, and we asked some questions about a game called Set, and just answered these mathematical questions just for fun, and quite a few of them came out to be a lot easier than it sounds. It's a fun game. Any other questions?
Can we play?
Can we play? Not right now. Maybe towards the end of the year. I don't have a copy of that game, so best explain that. Here we go. Here. So, TP14, if we were to follow the formula, that'd be 20 factorial over 20 minus 14 factorial. And 20 factorial over 6 factorial. Means this would just be 20 times 18, 17 times 16 times 15 times 14, 13 times 12 times 11 times 9 times 8 times 7 times 6 all the way down to 321 divided by 6 factorial. This and this are identical factors, 6 factorial. So we have to just multiply all those numbers together. Or, I guess a couple of options. My calculator is wise to the factorials. You can just do 20, hit the math button over to PRB factorial divided by 6 factorial. Here's one way to go. Or it also knows about permutations. 20 permutations, 14. Same number. All right. If I see E15 on a test, I'm going to mark it wrong. Even if that's what the calculator told you in the calculator, you use the calculator absolutely correctly. E15, it doesn't mean anything except for to the calculator. I don't know why calculator makers have their calculators say that, but what does E15 mean? Times 10 to it. So we can take it to 4 decimal places, 3790 times 10 to the 15. If they have 3.3790 on the thing that you're grading and it says E15, okay, let it slide, but on the test or quiz, no dice. So, any questions about that?
Do you always want us to go 4 decimal places?
Uh,
Feels like a lot of us want, or I don't know, at least Carter and I did, like 3.38.
yeah, 2 decimal places is fine. That'll be my standard. If it's if you round this to 3, it's just so far off. It's bad. So, I like 4. I usually do 4 because if I have any more work to do with that number to multiply it by something, whatever, and you know I want to get another number based on that, then I want it to be more accurate than just 2. But 2 is fine. 2 is fine. Right, next. So according to the formula, this would be 25 factorial over 25 minus 6 factorial times 6 factorial. That's 6 factorial times 19 factorial. So that makes it 5 times 24 times 23 times 22 times 20 times 19 all the way down to 1. The 19 factorial will cancel all those factors from 19 on back to 1. Divide by 6 factorial. Let's see, this says 6 can cancel with 24. 4, that 4 can cancel with that 5. 5 cancels with 25. This 3 can cancel with 21. This 2 can cancel with 22. So if we're trapped in a desert island or something, we can multiply 5 times 23 times 11 times 7 times 20. Just that one times 20. And trying to find all the combinations of 6 out of 25 coconuts on a desert island. Then that's how we would do it. But if we have our calculators, which you should always travel with your graphing calculator, just in case something like this happens. Right. Then we would just do 25. Let's go grab our combinations, 6 at a time. 77,100. And we should get the same if we multiply all of this together. Never go too quickly, just let me know and stop me and ask a question. Alright, so if there are 10 trumpet players, which apparently in band there are many, many trumpet players.
Yeah,
11.
12.
Yeah, a lot. And maybe I don't understand how chairs work, but hearing my mom talk about chairs from her high school band experience, it sounded like one person was first chair, second chair, third chair. But apparently, you guys have multiple people in first chair. I don't know how that works exactly. I'm not a band teacher. I don't know anything. But let's assume that one person is in the first chair, second person is in the second chair, another person is in the third chair. So we're taking from 10 people, 3 at a time. Whenever we're taking some out of a small group out of a large group, we're always going to do combinations and permutations. When it's that simple, then it's that simple. Taking some out of a larger group, we're going to do 10 something 3. We just have to decide, is it important, the order, or is it not important? Not important. Is it important, right? Because as Misty pointed out last class, I think it was, there are positions to fill. If there are positions to fill, then the order is important. If you have president, vice president, secretary, first chair, second chair, third chair, first place, second place, third place, if those positions have some kind of a name or importance or designation that makes them different from each other, then yeah, order is important. Okay. So what do we use? Permutations or combinations? permutations, that's when order is important. 10, P3, there we go, 720. So, all of you have finally made it to a safe stronghold, but you're running low on supplies. How many ways are there for 4 of you to be put into a group to go out and search the nearby town? Familiar with this scenario? Yeah. Happens all the time. But that's the kind of thing you need to think about when you're in a post-apocalyptic world and you've survived. This is how you keep surviving. How many ways can we do that? We're taking 4 out of a group of 12. Is order important?
No.
Nope. A group of 4 is a group of 4. There's not a leader of this group. Now, if I had written it that way, then it would become important. There would be a leader and a second leader, a third leader, and a guy that does most of the work. And they tell him what to do. So we use combinations. Order's not important. We just make a group of 4, group of 4, group of 4. 12 factorial over 4 factorial times 8 factorial. So this cancels some of this, leaving 12 times 10 times 9 times 12. 11 and 9. And 8 gets canceled by 8 factorial. 4, 3, 2, 1. 3. And 3 there. 2 will cancel with this. 10. 5. See, that's 9 times 5, 45, 495. Have I showed you the trick for multiplying by 11?
No.
That's kind of neat. It works for any number. If I want to multiply, so I knew the little trick, so I left 11, I multiplied 3 times 5 times 6, 9 times 5, that's 45. So 45 times 11. So if you're multiplying by 11, your product is going to be 1 digit more than the thing you're multiplying by 11. So your first digit is going to be 4, your last digit is going to be 5, and in the middle you have 4 plus 5. You can do it for 297 times 11. 2 is your first, 7 is your last, then you're going to add these together, you're going to add these together. So we'll add 9 and 7 to get this digit here. That's going to be 16, so we have another one to carry over here. 2 plus 9, 9, 10, 11, 12. So actually, that one goes up to 3. It's not the most amazing trick. I mean, you're basically just doing what you would do if you multiplied. If you set it up, 297 times 11, you're going to get 1 times 297, you're going to get 297. And then you're going to get 1 times 297 again, you're going to get 297. So you can see how we get the 9 plus 7 and the 2 plus 9. Right? So, just kind of cutting out the middleman and doing that stuff that you would do every time you multiply by 11. Anyway, any questions? No? Okay, score out of 16. I'll record those. 10.3. That's some basic probability. All right. Anybody for let's see. I pick a card out of a deck of cards. What's the probability of getting a king out of that deck? 4 out of 52. 4 out of 52. Okay. So this next part might be seen like, well, yes, that's clear. But if we can go back to this definition, there are times when this really helps us, even when the probabilities become a little more complex. So how do we define this fraction that we call probability? What goes in the numerator?
Apart provable.
That's a fraction in general. But how about probability? What goes in the numerator for probability?
Number of ways.
Number of ways.
Ways.
Number ways. Number of ways of what?
To do out of.
Seems tricky. Number of ways. So we're gonna need a word to talk about this thing. We're describing something that happens.
Number of ways
Can you think of a word whose definition is a thing that happens? Something happens? Huh? It's probably not a very good question. How about the word event? Okay. Something happens, it's an event, an event happens. Okay? So this is the described event. Okay? Events can be simple, getting a king. They can be complex, getting a hand with at least 2 spades. Okay? That would be an event. Okay? So events can be simple to complex, but that's what we call it. Number of ways the event happens. This particular event is a very simple event. It's actually a single outcome. Okay? An outcome is like the most simple. An outcome is once you've described the experiment, which is drawing a card out of a deck of cards, the outcomes are all of the most basic, simple things that can happen. Okay? So if I draw a card out of a deck of cards, all the outcomes would be drawing this card, drawing that card, drawing every single card that you can draw. That's the description of an outcome. Okay? This event's also an outcome, but if I wanted to get more involved, like, okay, what's the probability that I'll pick a card that is red? Well, that's not an outcome. That's a combination of lots of outcomes, right? And I need to be able to count all of those different outcomes and put them together somehow. Okay. But in the numerator we have here the number of ways that the event can happen, however I describe that event. Okay, down here is the total number of outcomes. So, what is the probability of getting a red card?
26.
26.
26 cards that are red. Okay, so this would be an event that is not as simple as an outcome. An outcome would be as simple as the king of hearts. Well, that's one of them red cards, right? So that's part of that event. Okay, the jack of clubs, that's not part of that event. So we're going to count all the ways that that event can happen. Well, that event is a combination of a bunch of outcomes, the outcomes that include all the red cards. And we can easily count them. There's 13 hearts, 13 diamonds. Those are all the red cards. It's a total of 26 out of 52. 52 is the total number of outcomes. The outcomes would be all the specific cards that I could possibly pick. So there will be times when we come back to this and we calculate our probabilities. Even when counting the number of ways the event can happen, it gets a little tricky. Like we have to use combinations and stuff. Okay. That's gonna be that. But if we can come back to this, this can make things a lot easier. So let's talk about some probabilities. See if you guys are on board. Let's pick some numbers. Well, let's pick one number from 1 to 50. What are the possible outcomes of picking a number from 1 to 50? Remember, outcomes are the most basic thing that can happen. What's an outcome of picking a number from 1 to 50? Just picking a number, no cards.
Oh, one number.
Okay, that's a description of the experiment. What is a specific outcome that could happen? What could happen? Pick a number from 1 to 50, what could be the result?
Any number from
Which one?
Anything.
You haven't told me any outcomes yet. You've just described generally what the
12.
experiment. 12 is an outcome. Okay.
Oh, that was difficult.
12, the number 12 is an outcome, you pick the number, that number turns out to be 12. What's another outcome?
39.
39 is an outcome. Okay, so these are all the outcomes, it's the most basic. So if I get any more general in describing what's happening, I'm talking about an event. So what's the probability, I'm going to state an event. What's the probability that a multiple of 12, probability of picking a multiple of 12. So I have to count all of the outcomes that fit into that event, divided by the total number of outcomes. How many outcomes are there possible? 50. I'm going to pick one number from 1 to 50, so there's definitely 50 possible outcomes. We counted how many ways this event can happen yet? What's one outcome that is part of this event? What's that? 1.
12.
12.
24.
24. Okay,
36,
12, 24, 36.
48.
48.
21. 4.
Those 4. 4 times 1, 4 times 2, 4 times 3, 4 times 4. 4 times 5 is too big, it's past 50. So we have 4 possible outcomes in this event. That's how many ways this event can happen. And we can get 2 out of 25, and simplify it down 2 out of 25. What's the probability? We pick an even number. Hmm?
25 out of 50.
25 of them are even. Okay. You sure? No, wait. What's that? You sure exactly half?
No.
You're not?
26.
26? Well, that's something you got to think about. You know, it seems like half, but what if we don't have an even number of numbers to pick from? Maybe there's one more odd or one more even. But in this case, yeah, there's 25. Oh, right. 2 is even, 4 is even, 6 is even. So it's like they kind of break it up into groups of 2, 1 and 2, 3 and 4, 5 and 6, 7 and 8. And that last group ends in 49, 50. Right? So 50 is that second part of that group, and an odd and then an even. So yeah, there's 25 even numbers out of those 50. So 1/2. 50-50. What's the probability of a composite number?
Oh, what?
Composite number. So, if we add the probability that we get a composite number plus the probability that we get a prime number, what's left? 1 plus the probability that we get the number 1. What should all that add up to?
50.
It's probabilities, it's not the number of outcomes, it's
I
probabilities.
don't know. This hurts my head.
What's the highest probability you can have? The highest probability you can possibly have.
One.
What? 1. Or what'd you say before that?
All of them.
Oh, all of them. Okay. 1 is the most, right? We can have a 0.5 probability you could have, or 1/2, or whatever. But if we add up all the probabilities of all the possible situations, we can only add up to as much as 1, or 100%. Those are the same thing. 100% or 1 in decimals is the biggest. So it would add up to 1. Okay. This probability that we'll get a composite, that's kind of hard to count all. We just have to go through all of the things that are composite numbers. Or we could go through all the prime numbers, which we're guessing there are fewer of, and then take all that away from 1, and we'll get the probability that we'll get a composite. So we'll subtract the probability that you get a prime from both sides, and we'll subtract the probability that you'll get a 1 from both sides. So it's going to be 1 minus the probability of, let's just call it prime, like that, minus the probability of getting a 1. Okay, so the probability that you get a prime number, now we have to count all the prime numbers, keeping in mind that 1 is not prime, and it's not composite. That's why it's its own outcome. So let's talk about the primes together. 1's not it, is 2 a prime?
No.
Yeah, it's prime. It's funny, it's even, but it's also prime. It's only 2 times 1. How about 3?
Yeah.
5. We're not going to even consider even numbers right after 2. So 7? 9? No, that's 3 times 3. 11?
Yes.
13?
Yes.
15?
No.
17?
Yes.
19?
Yes.
21?
No.
23?
Yes.
Yeah. 25?
No.
No, 25 is 5 times 5. 27?
Yeah.
No.
Prime?
No.
9 times 3, so not 27. 29?
Yes.
29. 31?
Yes.
31. 33?
No.
No, that's 11 times 3. 35?
No.
No. 37?
Yeah.
37. 39?
No.
No, that's divisible by 3. 39 over 41?
Yeah.
41. 43?
Yes.
That's prime. 44, 45?
No.
No, 47?
Yes.
49, okay. 49?
No.
What's that?
7 times 7.
7 times 7. Okay. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 15. 15 of these guys are prime between 1 and 50. So subtract that 15 out of what probability?
50.
15 out of 50. Alright? Take it from 1 to 50. What's the probability that you'll get a 1? 100?
No, 1 out of 50.
Probability that you'll pick the number what?
49?
How many 1s are there?
4.
How many total are there?
50.
Not likely that you'll pick a 1, just on a random thing, right? So if we put these together, we'll have the probability that we get a composite. I just want to use this example, labored as it might be, to teach you about complementary probabilities, just like there's complementary events. So we got 50 out of 50, that's a 1. Minus 15, well, let's just say minus 16 out of 50. Because we got 15, negative 15 minus 1, negative 16. So that comes out to be 34 out of 50. Seems right to me. We can simplify this. This would be 8, 17 out of 25. 17 prime, so it's not going to simplify any more than that.
Good work.
Yeah.
Plus.
So the probability that you get a composite number is 17 out of 25. And we remember to, hopefully we remember to keep in mind, if it seems like the probability you're trying to calculate is a lot of work, think about calculating what else could happen, everything else that could happen. It might be a little less work, and then take that away from 1. That way you won't have to do so much work. Okay. Let's talk about the lottery, because I like to talk about lotteries and hopefully convince you never to play the lottery. Okay, it's so unlikely. So first let's calculate the probability of winning the lottery. Do you know how the lottery works?
You get screwed.
That's how it
You
works.
get a ticket and then you hope you win money.
Alright, so you buy a ticket and you hope you win money. You hope you have a winning ticket. Okay? Now, how does that ticket win?
Has like numbers.
Has some numbers. How many numbers do you pick?
5.
5. Okay, so you pick 5 numbers. What numbers do you have to choose from? 1 through, I guess it's 50, something like that, 52, something like that. 50?
52, I think.
52, let's go with 52. I don't know why 52. Huh?
But how am I supposed to know? I don't.
Sometimes people know things, they just learn them, they just get stuck in their brain.
Yeah,
and it's
maybe you
done.
saw it one time and then.
Yeah,
Yeah,
maybe you saw it.
maybe
Oh.
watching
Oh.
movies, lottery buying.
Yeah, movie.
stuff.
I don't
A
fault you
movie?
for it, but maybe you
Been
did.
at the
Let's go with
store
52.
and someone bought one in front of you.
So we pick 5 numbers
Never.
from 1 to 52, and we have to get the right numbers. Is it important that I get the right numbers in the right order?
Yes.
It is important, so order is important.
Yeah.
Okay, so we're going to get the probability that we win the lottery. Alright, first in the numerator, the number of ways that this can happen. How many ways can winning happen?
1.
Very good. 1. If you have 1 ticket, it has 1 way to win. Okay. How many possible combinations of 52 numbers, or how many permutations of 5 out of 52 numbers are there?
Oh, sweet Jesus.
Huh? How do we calculate it? Yes, how?
52.
You don't just hold it in your hand, you gotta press some buttons. 52.
Permutation.
Permutations.
5.
5.
That's a big number.
Oh.
What is it?
311.
311,875,200.
Good at talking.
I hope I picked that out of all the mess of
Yes.
numbers that I was
Yeah.
hearing.
You're right.
People that do, I'm jealous.
Okay, 311,875,200. Okay. So your odds are very bad. Okay, the probability is very bad that you will win. So why do people play?
Because they're
Because they
They
want
got
the
a
money.
chance. There's a chance somebody's gotta win, right?
No.
Somebody's gotta win. That's true. Somebody does have to win. The thing that people fail to understand is that you, by buying a lottery ticket and thinking you're gonna win, you're basically saying, I am betting on me being the one person who wins. And also, it's not true that somebody has to win. Somebody eventually will win. But actually, there are weeks in a row, sometimes, where nobody wins. Right? Because you have to get the right number. It's not a raffle. You don't buy a ticket and they throw your name in a hat and they pick your name out. You have to get the right numbers. So if the numbers don't come up for anybody, nobody wins. That's how we get into these multi-hundreds of millions of dollar jackpots, because people don't win multiple weeks in a row. And when it's out of 300 plus million possible numbers that you can make, it's really unlikely that you'll walk into a convenience store, give them 5 numbers, that then this machine will pick randomly. You're betting on yourself, and you're a very bad bet. Now, if you were allowed to bet on somebody in the United States winning this week, that would be a safer bet, but not a completely, 100% guarantee. So don't play the lottery ever, unless you want to play once just for the excitement when you're 18 or something.
Just go play bingo when you're 18. That's what my sister
Yeah,
did.
okay. At least you have a chance there. There's some skill involved. It's really fast, I guess. So, anyway, really, really bad probability of that happening. But in this case, we have to bring our combinations, permutations into our probability knowledge, right? We've got to put everything together. To count the number of ways that 5 numbers can be picked from 52, we have to use our permutations in order to do that. So we're all rolling it all together into one thing. Another thing. This is an interesting question. I want you to think about this question, and if you have an answer, I want you to have a reason why you have this
Wait, was
answer.
that the answer?
That was the answer. That's the probability that you'll win the lottery. If that's how the lottery works, 52 numbers, you choose 5 in the right order. That's how it works. That's the probability. There are some, I think the Powerball, you actually pick 4 numbers white, 1 number red, The first four numbers, I think, are from 1 to 52. The last one's out of fewer. I don't know. And of course, they try to entice you because you might win like, well, $100 if something happens, like you have two of the right numbers or something like that. But they're winning like every time. Plus, they're taking some of the money for themselves. Anyway, here's a question. And again, if you have an answer to this question, please answer it with a reason. Don't just shout out guesses, okay, with no reasons at all. Here's the scenario. You live in a house, got it? And you leave your house at some point in the morning to go to school. Okay, let's say the hours that you leave are between 7 and 8. Sometime between 7 and 8, you leave. Okay, you've got to make this simple, otherwise. So, and assume that the time that you leave is somehow randomized. Okay, maybe the night before you randomly pick an exact time down to like the very smallest delineation of time that you can leave. Just thousands or millions of a second or whatever. You leave exactly at that time. Okay. Then also between 7 and 8, okay, you're leaving at some point. Also at some point, the paper is delivered. At some point between 7 and 8. Okay. So sometimes you'll leave before the paper gets there. Right? You'll leave at 7 and it'll get there at 8. Or sometimes you'll leave after the paper gets there. You leave at 8 and the paper arrived at 7, so there it is sitting in a bush somewhere outside your house when you leave. So you take it with you. So what's the probability that you will get to leave with your paper in hand? Which means that you need to leave after the paper has gotten there. Right? Even slightly after. It needs to get there and then you leave. It's there so you can pick it up and take it with you to school. Right? So the trouble with this is there's so many different possibilities for when you might leave and when the paper might come. So try and calculate it in a way where you say, okay, in how many different ways, at how many different times can I leave my house? What's the answer to that?
A lot.
60.
Well, okay, there's 60 minutes, but what if I leave at 7:01 and 30 seconds? Well, now there's more than 60, right? Now there's 120 if I do it 30 seconds. But what if I cut it down to every second? Well, there's 3,600 seconds, so there's 3,600 possibilities. But what if I leave it half a second? So how many different ways, different times can I leave my house?
Infinity.
An infinite amount. There are, when you say you can leave this time, what if you leave at 1/1,000,000th of a second later? Well, that's a different time. And the same for the newspaper. Okay. And then we have to figure out how many ways are there for me to leave after my paper arrives. How often could that happen? Now becomes a very tricky problem. Right? Trying to count all those things like they're quantifiable events or times that you can count up, it becomes an impossible problem. Right? You have to approach it in some other way. Okay, this is going to be similar to like number 39. Okay, it's archery. We're gonna shoot a dart at a target, but if I'm shooting a dart at a target, there's also an infinite number of possibilities. I could hit the target right here, or halfway between, or halfway between that, or halfway between that, and now there's a infinite number of possibilities. So what do we do? Let me show you. So we're going to draw a graph.
Close the door, it's a disturbance.
You can do that. All right, so let's say that this is the time that you leave, and that this is the time that the paper arrives. This is you leaving, this is the paper getting there. Or we could leave between 7 and 8. So on this axis we have 7 a.m. to 8 a.m. On this axis the times are the same, 7 and 8. All right, so you get the idea. So let's put a point on here, like right there. So what does that point represent? It represents something on this axis and something on this axis. Let's just estimate it. What does it look like on this axis? Looks like 40? 740. All right, there's a reasonable guess. Looks like you've left at 740. Okay. And then, what about this? That's 725? Oh, I don't know. 730 would be right in the middle.
7:15.
I would say
I'm going to go
7:17.
7.
Let's be real.
Okay. So this is you leaving. This is the paper getting there. Can you take the paper with you? Is the paper there when you leave?
Yeah.
It is there when you leave, so you can take it with you. Okay. What about now?
Yeah.
Can you take the paper with you?
Yes.
Why?
Because you still leave later than it arrives.
Leave later than it arrives. What if I put my point here?
No.
No, you leave earlier than it arrives. Like your distance to the point is smaller than this distance to the point, right?
Yeah.
Okay. How about right here?
That's pretty close.
Okay. What about right there?
I don't know, it's still pretty close.
No.
But you're coming out. He's walking out.
Huh?
in the way.
Oh,
No.
No.
okay. Could we maybe then imagine, because we're limited, that maybe this is when, this is a scenario where, like, you're walking out of the door, the paper, and it comes, you catch it in your hand. It's the exact same time.
Wow, that's crazy, that's scary.
Yeah.
Okay?
You'll be back.
So, this line, ooh, what's supposed to be a line? This line, okay, represents all the time when exactly the same time. You leave, paper arrives, you catch it. Anywhere on that line is you catching the paper in hand as you walk out of the door. Anything above it, what?
Means you don't get to take the paper.
Nice. Anything above it, no paper. Okay, and
And below it means you get to bring your paper with you.
below it, yes, paper. Well, so how do we talk about the probabilities? Well, if we were to kind of block all this in, we would kind of make a square, right? And all of the points that fill in this square would be all the possibilities, right? How many of those possibilities are you taking paper with you? Half of them, right? So we don't so much have this many points versus this many points, we have this much of the area versus this much of the area. We have the total area, which all the points, all those infinite, beyond infinite number of points, that's all the possible things that could happen. The paper arriving and you leaving, that combination of those two times. Along here we have a separating line where they happen at exactly the same time, and down here we have you getting the paper. And you can see this is a diagonal line, it cuts the square exactly in half. This half is you leaving with the paper, this half is you not getting to leave with the paper, so the probability is 1/2. So we turned a seemingly impossible problem into a problem that we just compare areas. So if you have something like that, which is basically like, here I give you this area and I want you to shoot an arrow at it, like the number, whatever it was in the book. Basically asking you to shoot an arrow randomly somewhere on this square and it hits a random point like right there, and that determines the combination of the times that the paper gets there and that you leave. In this scenario, where that arrow hit, you get to leave the paper because it got there after, or before you left. Here, if your arrow is there, no, you don't get to leave the paper because the paper got there after you left. Okay? But half of the available points are here, half the available points are there, so half the probability is going to 50-50. We can do that with the archery target. Do it with darts, we could do it with squares and triangles and circles and anything that we can find the area of, if that's the kind of scenario we're looking at. Then we can turn it into that. Now I'm not gonna, this is a pretty tricky problem that you have to kind of think outside the box, turn it into an area problem. If it's an area problem, it's clearly an area problem. There is a shape, you need to find the areas and compare the areas. The smaller area to the larger area, you find the ratio of how many points are here to how many points are here. So we call that a geometric probability. Which is neat and fun and stuff. So we've got basic probability, the number ways event happens over total outcomes. Then we've got the complement. Basically that means subtracting all other probabilities from 1. 1 being 100%. All of the total probabilities that could ever happen. The highest probability you could have would be 1 that would be guaranteed to happen. Right? And lastly, geometric probability. That would be small area over total area. We were given a triangle and a circle that was inscribed in the triangle perfectly. And we were given some measurements about these two things somehow. If we want to know what's the probability that we shoot an arrow at it or throw a dart at it and we hit one of these outside of the circles, then we need to find the area of this, and then divide it by the area of the whole triangle. And then we'll have a probability that we'll hit that with one of those small areas. That one's a little bit tricky. They're going to give you squares and circles, maybe some triangles. They're going to give you all the measurements that you need. Remember that the area of a circle is pi r squared. Area of a rectangle is length times width. Area